everyone, welcome to our channel NCERT Science. So today's video is a continuation of the NCERT Science for Class 9 series that I've been doing, and today we're going to talk about force and laws of motion, which happens to be the 9th chapter of NCERT Science for Class 9. Alright, so in the previous chapter we read about motion. Now we're going to talk about force and laws of motion. Alright, so before I start the lesson, I just want to do my standard speech, as always. So I want to mention three things. The first thing is that this video will be helpful for those preparing for your CBSE exams, NTSE, NEET and JEE. Alright, so for NEET and JEE, this will serve as a foundation, and a good foundation is always good, right? Alright, so this is going to be helpful for a lot of people. The second thing is that I will be presenting in my own words, and I have pictures taken from the NCERT Science textbook that I found online on NCERT's official website, and I want you to take your own notes, and I encourage you to take them in your own words, and I want you to actively take notes and learn, because that will help you remember better in the exam. Alright, and the third thing is that I intend these videos to be very short, so that you can, like, less than 1.5 hours, so you can watch them even before the day before your exam, or whenever you want to. Alright, so if you feel that I'm going fast, feel free to change your YouTube settings to 0.75 speed. Alright, so with that said, let's start with chapter 9, force and laws of motion. Alright, so this is all, I think the whole first page is an introduction. And before we start the lesson, I just want to start with a question. I want to ask you, what causes motion? So throughout the last chapter, we were talking about how we were talking about the different types of motion. We were talking about graphs. We were talking about equations of motion, all of that. But what causes motion? Like, if you look in front of you, the table is not moving. The table is not running away, or it's not walking, right? And it's not moving. The same goes with your tube light, or your table light, right? Or your pen. Unless you are moving it, the pen is not moving. Unless you're moving it, none of the furniture, or your bag, your school bag, or your clothes, none of them move, right? So even us, unless we want to move, we won't move. Even though someone says, hey, could you get me that? If you don't want to move, you just don't move, right? So what causes motion, whether it's in us, or if it's in other non-living objects, or if it's even in other living objects, what causes motion? The answer to that is force. Alright, so some force, whether internal or external in case of non-living things, but internal or external for living things, force causes motion. Alright, so we're going to talk a lot about force in this lesson, and we're going to talk about the different laws of motion. So the 3 laws of motion of you might be very familiar with, and I think most of us are thinking right now, we're like, oh no, not these 3 laws of motion, because since childhood we've been listening to the 3 laws of motion. You know, it's all hyped up. I feel that's what I felt when I was doing 9th grade NCERT Science. NCERT. I used to think it was very difficult because of all the hype that people create. Whenever they want to ask something about science, they say, what's Newton's laws of motion? It's not that hard. It's actually very easy if you understand what's behind it, alright? So right now I'm very excited to start this lesson, because I want to take that out of your minds, alright? That Newton's laws of motion are very easy, and I don't know why That's what you're supposed to think. These laws of motion are very easy. I don't know why people have been hyping them up since I was born, right? I want you to think that. And as I say in every video, you should remember that you can do this and you will be able to do it. Alright? So we have a few pictures here that talk about how a force is causing motion in an object. Alright? So we have a boy who's pushing a shopping cart here. The cart is not moving by itself, right? So a force is moving it. And what is that force? The boy pushing it is the force. Alright? And this cart is moving in the direction in which the boy is pushing it. If you have a table and if you have a desk and if you're trying to pull out a part of your desk, that is because of this. You will hold it by the handle and you will pull it out so that you can put something inside it. And it is moving in the direction of the applied force, right? Someone playing hockey, the ball is not going to move by itself. The girl is hitting it with the bat, but she is hitting it and applying external force in this direction, and the ball is going to consequently move in that direction. Alright, with a spring, unless you so if this is a spring, and if you hold one end here and the other end here, and you pull them in opposite directions, so this is going this way and this is going this way, what do you see? You will see that the spring has expanded, right? It's longer than how it has been in its natural state, right? So that's how the spring is moving. You take a flexible ball, alright, a spherical ball, and then you compress it from both directions. What's happening to the ball? It's getting compressed, right? It's moving in the direction of the applied force. So they're all examples, all of these examples and every other example that you can ever come up with, all of them prove that objects move. The motion in objects is caused because of an internal or external force. Alright? In some cases it can be both internal and external. Alright? So with that being introduced, let's talk about balanced and unbalanced forces. Alright? So this figure shows a brick that's on a table, and two forces are being acted in in opposite directions. Alright, so there are two strings X and Y, and they are being pulled from each side. So they're being pulled in opposite sides. Alright, so if you just move, if you hold X, just X, not Y, and pull by the string X, you will see that the brick shifts to the right. Similarly, if you leave X, if you leave the X side of it, and if you hold the Y side of the string and you move it to the left, you will see that the brick also moves to the left. However, if you hold X and Y together and you start pulling them in both directions, the block will not move, right? So by both directions, I don't mean apply a lot of force on the X string and not a lot of force on the Y string. If you're pulling on both of them in opposite directions using equal force, you will see that the block does not move. Alright, but so why is that happening, right? Why is that happening? That's what we're going to see. Alright, so forces in which there are equal forces that are acting in opposite directions are called balanced forces. Alright, so balanced forces are the forces that do not change the state of rest or the state of motion of an object when applied, when equal force is applied. Alright, so in this definition the keywords are do not change and the state of rest or state of motion. Alright, so the brick is at state of rest right now, that's why you're not able to move it. But what if someone is already, or something is already moving, and you apply equal forces in opposite directions, the object will keep moving, it won't stop. So if it is in a state of rest, it will continue to be in a state of rest under the influence of balanced forces, and if it is in a state of motion, it will continue to be in the state of motion under the influence of balanced forces. Alright, so now that we talked about balanced forces, what do you think unbalanced forces are? Alright, so unbalanced forces are just the opposite of balanced forces. So if balanced forces were equal forces that were applied in opposite directions that caused no change in the state of rest or of motion um, in an object, what is the definition of unbalanced forces? Alright, I want you to think about it. Okay, so unbalanced forces, pause the video, think about it, write it down in your own words, and let's see how we did. Alright, okay, so now let's talk about what unbalanced forces are. So unbalanced forces are the forces that are not balanced, first of all. Alright, and unbalanced forces cause an object to move in the direction of the applied force. Alright, so applied force, I mean the direction at which a greater force is applied. So right now let's think about it mathematically. If there is x amount of force on that is being applied on the right side of the object, and x amount, I mean the same amount, x and x are same, and x amount being applied on to the left side, they're balanced forces, so they don't cause any change. Alright, however, if you have x force on to the right and y force on the left, and if it is given that x is greater than y, then the object moves to, so the object undergoes an overall movement to the right. Alright, so let me do color code here. If x is greater than y, this is what is going to happen. Alright, switch colors here. If x is less than y, the object will have an overall direction of motion towards the left. Alright, and then we do the third situation. If x is equal to y, then the object will stay where it is. Alright, so if x is greater than y, that means if these two are unbalanced forces. Alright, so unbalanced forces causes an object to move in the direction of the direction in which the applied force is greater. So here in case 1, x was greater, so it moved towards x. In case 2, y was greater, so it moved towards y. Alright, that is what I mean by in the direction of the greater force. Alright, so that is the definition of unbalanced forces. Alright, so forces don't always have to be us moving it, like animals or humans or whatever. There are also naturally occurring forces, like if you move your pen across the table, it will not move forever once you move it and leave it. Why is that? It will stop after a while. And why is that? Because of the presence of friction. Alright, friction is a naturally occurring force that is resistive. That is a resistive force, and it acts in the direction opposite to the applied force. Alright, so if force is being applied, like, so if this is an object here and force is being applied in this direction, alright, so I mean if the greater force is being applied in this direction, the object will move this towards the right, correct? But frictional force will act against the object in the direction which is opposite to the direction of the greater force. Alright, so remember, understand and remember this very carefully. Frictional force is the resistive force that acts against the object in a direction that is opposite to the direction of the greater force that is being applied. Alright, that is frictional force. Alright, so how to see whether it's whether given motion is balanced or unbalanced. Alright, so here we go. Here they're moving x amount, they're moving the box by x amount here to the right, and the same x amount, it looks like the same, right? So if I erase these, don't these arrows look like they're the same size? right? So unless they say this figure is not to scale, we cannot, so usually we cannot come to such conclusions as a good math or physics student, right? But they seem about the same size, right? And they're moving in opposite directions, so this would be balanced. Same here, they seem like they're of the same force and they're acting in opposite directions, so this is also balanced. So here we have a greater force to the right and a lesser force to the left. We also have an additional lesser force but to the right, but these two add up to be a lot greater than this one here, so this would be unbalanced force. Alright, so uh, so one thing you have to remember is that under balanced forces, if an object is if an object is at rest, it will remain at rest, and if the object is in motion, it will continue with the same. It will continue into moving in the same direction. All right, but if it is unbalanced forces, the motion of the object either continues or stops to a rest uh, based on which side the force is being applied at a greater extent. Alright, so just like that we finished the introduction and we're at the first law of motion. Alright, okay, so this is all an introduction. You will not need any of, it will not be tested, but I recommend you to read this part, right? Because that will help you understand the subject better. It's there for a reason, right? I'm not able to cover it because, like I said, I want these to be videos that you can watch the night before your exam or something. And you guys wouldn't want me to go through every line in the textbook, would you? No, right? So I'm going to be covering the important concepts, but I recommend you and I highly suggest you to read every line of the textbook because this is NCERT. We never know what sentence will be pulled from which part of the lesson to be tested on, right? I'm explaining the concepts. I need you to study the theory and the memorizing parts of it, alright? Okay, so this is just a basic proof of this, alright? So Newton studied Galileo's ideas on force and motion, and he presented the three fundamental laws that are known as Newton's laws of motion, alright? So the first law, Newton's first law, states that an object remains in a state of rest or of uniform motion in a straight line unless compelled to change that by an applied force. Alright, so this is one way to say it. Another way to say it, an easier way I feel, for laws of motion, you need to write down whatever your teacher told you to, alright, or whatever the textbook has if your teacher didn't mention anything special. But in order to remember it, this is a good way of remembering it. An object at rest continues to be at rest, and an object in motion continues to be in motion as long as there is no external unbalanced force being applied. Alright, so doesn't that make sense? Doesn't that make much more sense? If an object is at rest, it will remain at rest, and if an object is in motion, it will remain in motion unless under the influence of an external balanced force. So it will remain in that state of rest or of motion that it was in unless an external unbalanced force is applied. So unless an unbalanced force is applied, an object at rest will remain at rest and an object in motion will remain and continue in its direction of motion. Alright, that is the first law. If that will help you remember better, by all means, try to remember that, but you also need to have that law memorized that your teacher told you to, or if your teacher didn't tell you anything, maybe just go by the textbook. if you are having to write the law in your exam, theoretically, do not move away from the textbook or your teacher unless they specifically told you that you can write any definition, any law, as long as it makes sense. Alright? Okay, so in other words, all objects resist a change in their state of motion. Alright? Unless there is an external unbalanced force, they will not change their state of motion, whether it's rest or motion. They're both states of motion, right? No motion is rest, and no motion is a state of motion, right? So rest and motion are states of motion, and all objects resist a change in their state of motion as long as, unless there is an unbalanced external force. Alright? So we have Galileo here that you can read for fun. Alright? So this is all an easy way that, to explain it to you and to help you remember easier. The whole second part of this topic is just a few examples that will help you remember better. And now we have an activity. I think this is the first activity. Yeah. So this is the first activity. Very fun activity, I feel. If you don't like carom board, then it's not on me, but I like carom board, so I like this activity, right? So this is a very fun activity. If you want to play sometime, just whoever you're playing with, this is a part of my physics assignment. No, don't say that. Go study. All right. Don't say I watched in the YouTube videos. Whoever was explaining told me to play carom board. Do not. Do whatever your parents tell you. All right. Okay, so activity, there's another activity. This is also a fun activity that has been turned into a game. Last time I checked, it was a game. Alright, I don't know about now, but it was a game. Alright, and then we have another activity. They're all fun activities here in, I don't know if you can do this. No, you can do this, but be very careful because there's probably going to be water spillage and I don't want you to slip and fall and blame it on me. Alright? Okay, so we're talking about inertia and mass here. So until now, whenever I talked about motion, I said that an object moves under the influence of an unbalanced force, it moves in the direction of the greater force, right? That's what I kept saying. And I also talked about friction, which I said is a resistive a resistive force. So there is a resistance that is offered by an object to its change in state of motion. Alright, so whether it's going to stay in rest, stay in motion, or change from motion to rest or rest to motion, or whatever else combination that you can come up with, that is all because of an external unbalanced force, right? So if it is at rest, that's what I wanted to say. If it is at rest, it tends to remain at rest. If it's a balanced force, an object at rest tends to stay at rest, and an object in motion tends to remain in motion. That property is called inertia. All right. So how we learn is inertia is the inability of an object to change its state of motion under the influence of a balanced force. Alright. So under a balanced force, an object at rest will stay at rest, and an object in motion will remain in motion. I am repeating this multiple times because I want this statement to sink in your head, so much so that it has been over a year since I said this statement, but I still say it as just as I have said it on the first day, right? As though I have learned this statement just today or something. That is how much this statement should sink in your head, alright? If you want to take physics as a serious subject, I mean. Alright, so alright, so here we have a situation. Do all bodies have the same inertia? This is the question. So the answer is no. The answer will be no, it depends. For example, try pushing a book or try pushing a book down a table. How much force does that take? And how much did that book move? Alright? And then go try pushing your desk with that same force. Did it move as much? Not at all. Right? It probably moved a little, but not so much. Now go try pushing your bed with that same amount of force with which you pushed your book. Did that move? Not at all. Right? That bed did not even budge an inch. I mean, if you were doing it with the same force that you pushed your book, it wouldn't have budged. There are high chances of it not moving, right? So that shows us that not all objects have the same inertia. There are different objects and each of them have different inertia. They might be very similar, like pushing a pen and a pencil might take the same effort, right? A few objects have similar inertia, but not all objects have the same inertia. Alright? So a heavier or a more massive object has a lesser tendency to change its state. So if you push a truck, it won't change, it won't move just because you pushed it. But if you push a toy car, there is a good chance of it moving, right? So if you compare a toy car with a truck is more heavier. I mean, a truck is more heavy. A truck is more massive than the toy car, right? So more massive and heavier objects are less likely to change their state of motion under a weak external unbalanced force. All right, but that is the opposite for lighter or less massive objects, which have which can be moved or whose state can be changed. Yeah, I can put it that way. There are good chances of less massive or lighter objects being changed about their state because of an external unbalanced force that is weaker, right? Weaker. I don't mean very weak, but I mean weaker than that we're using for the massive object. Alright? Okay, so the mass of an object is a measure of its inertia. That is a very important statement. Alright? So the mass of an object is a measure of its inertia. The heavier an object is, the less inertia, the heavier the object is, the less likely it is to move under the influence of a weak external unbalanced force. Alright? So we have the first few questions of this chapter. We have the first 4 questions. I want you to try them on your own. And if you are unable to solve any question or if you're stuck on a question, feel free to go back to that part of the video where I explained that question. Alright? So we finished the first law of motion. Woohoo! Right? Alright, so the second law of motion, let's start with the second law of motion. So they're just giving like a recap of sorts of the first law. The first law of motion indicates that when an unbalanced external force acts on an object, its velocity changes. And that is, the object gets an acceleration, right? It's moving, or it's changing from rest to motion or motion to rest. That is because of a change in velocity or a change in acceleration, right? So let's now study about acceleration of an object, and let's see how that acceleration depends on the force applied to an object and how we measure a force. All right. So let's observe a few situations. And during the game of table tennis, if the ball hits a player, it does not hurt him. On the other hand, when a fast-moving cricket ball hits the spectator, it may hurt him. It will hurt him. Alright? So, similarly, a truck at rest does not require any attention when parked along a roadside, but a moving truck, even at speeds as low as 5 meters per second, may kill a person standing in its path. Alright? So what does that tell? What do these situations tell us? that a small mass, a very small mass, so like a bullet, it has a very small mass, right? A bullet, it might kill a person when fired from a gun. So all these observations suggest that the impacts produced by objects depend on their mass and velocity, not just their mass, but also their velocity. Because the first two situations, the second situation talked about the mass and the talked about the difference in force in regards to mass, but the first and third situations, and even the second situation to an extent, talked about the importance of mass and velocity in an object to make a difference in its force, right? So a bullet is very light compared to a truck, or compared to a cricket ball, or compared to any other heavy object, like even your laptop, unless it's really sleek. Um, but a bullet is light, it's relatively very light, but when it is fired from a gun, that velocity is enough to kill a person or to kill anything, right? Um, so that's how velocity and mass play an equally important role in determining how the force of an object might affect others, right? Alright, so uh, momentum, that is what we're going to learn about. Momentum is the product of its mass and its inertia. Alright, so a mass and its velocity, So momentum, which is represented by P, the lowercase letter P, is a mass of, it's the product of mass and velocity. So here we have the equation P equals mv. Alright, that is the definition of momentum. And momentum has both direction and magnitude. So what kind of a quantity is it? Pause the video and tell me very quickly what kind of a quantity is momentum. If you said a vector quantity, great job, because it has both direction and magnitude. That's what we were talking about in the previous video. If you didn't check that video, go check it out. We had fun going through that lesson. Alright, so since the application of an unbalanced force brings a change in the velocity of the object, it is clear that a force also produces a change of momentum. Alright, because momentum is the product of its mass and its velocity. Velocity is a change in speed, and a change in speed is caused by a change in the amount of force applied. So indirectly, force applied or an external unbalanced force causes a change in the momentum. Alright, so let's consider a situation in which a car with a dead battery is to be pushed along a straight road to give it a speed of 1 meter per second, which is sufficient to start its engine. If one or two persons give a sudden push to it, it hardly starts. But a continuous push over some time results in a gradual acceleration of the car to this speed. It means that the change of momentum of the car is not only determined by the magnitude, but also by the time during which the force is exerted. Alright, so this may seem a little counterintuitive for a few people. When I first did this, I was thinking about a totally different situation. I was imagining like a person standing at the edge of a pool or something, and if we suddenly and abruptly push them, give them even a small push, if they're not expecting it, they will fall directly into the pool, right? That's a fun sight to watch. But that is what I used to imagine when I was studying this, and that's how come I always had this doubt and I always had this confusion. But they're talking about the influence of mass and velocity along with the influence of time in the alright, so imagine that same person standing a little away from the pool. If you give them that 1 second push, that won't be enough. You might have to push them longer, even if it was with the same force, right? So that is how important time is. Along with mass and velocity, time is also important in determining how that force affects its surroundings or the people around them, alright? So the change in momentum of an object also depends on the time rate at which the momentum is changed, alright? So the second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. This is a very important statement, and I think most teachers might want you to memorize that same statement, but I think you should ask your teacher to ask and see if your teacher still wants to follow the same definition that is provided in the textbook, or if he or she wants to make it easier for you to remember. It's up to them. I do not want to say anything that will make you lose your points. Alright, so we're talking about the second law of motion, and let's see how we derived it. Alright, so here we have the change in momentum. If initial momentum was P1 and final momentum was P2, the change in momentum, let me put it as delta P, because change, alright, that's what we learned about in the previous video. Change is represented by delta. So delta P is equal to P2 minus P1. And what is P2? MV. So P2 would be the same mass. So mass will remain constant, and for P1, which is the initial momentum, mass will remain constant as well. So for initial momentum, it would be initial velocity, which would be u, and for final momentum, it would be final velocity, which is v. Alright, so final momentum minus initial momentum would be equal to mv minus mu. Alright, so that would be, if you take m common, it would be m of v minus u. Now the rate of change of momentum, whenever you say rate, so this is something that always bothered me. When people say the rate of change of something per unit time, that is grammatically wrong. The rate itself talks about the influence of time in that, right? It's like saying something like ATM machine. ATM already has, the M in ATM is already machine. So when you expand that and you say ATM machine, it's like auto teller machine. There's no two machines, right? There's just one machine. So you say ATM. Similarly, you say the rate of change of something, of a quantity, but you never say the rate of change of a quantity in unit time. You either say the change of a quantity in unit time or the rate of change of a quantity. Alright, so whenever you say rate, there is the influence of time. So per unit time. So this will be the rate of change of momentum. And what did we talk about v minus u by t? That it is acceleration. So mass times acceleration is the rate of change of momentum. Alright, so and when does momentum change? When there is a force that is being applied. So momentum change, rate of change in momentum is directly proportional to the force applied. So if we take a proportionality constant k, F equals k m a, and this is the mathematical definition for Newton's second law of motion. Alright, so I hope that derivation was clear, because that is a very important derivation. If you didn't understand a part of it, feel free to go back and watch it again and again and again until you get that derivation. Alright, because it's a very important derivation, and I don't want you to miss out on derivations, especially when especially because I skipped through most of the derivations in the previous test. Alright, so force is equal to kma, or instead of mentioning k every single time you write the definition, we usually say F equals ma and we leave it at that. Alright, so what is the SI unit of force? What is the SI unit of mass? Kg. What is the SI unit of acceleration? Meter per second square. So the SI unit of force will be kg meter per second square, which is also Newton. Newton with a lowercase n, because it's the name of a scientist, and when we name something after a scientist, we begin the name with a small letter and if we are writing that their name as a symbol, we leave it in the uppercase form of it. Alright, that is the SI unit of force. Newton, capital N, or Newton with a lowercase n, or kg meter per second square. Alright. So the second law is always, so we have many applications of the second law of motion. One famous example is if you watch cricket a lot, you might be able to understand this pretty quickly. Whenever a fielder is catching the ball, right? So whoever is throwing the ball is throwing it across a long distance, across a large distance, right? Almost half the court or half the field, not court. So when they're throwing it across such a large distance, they use a lot of force because it has to travel until there, it has to overcome the air resistance that it goes through and all of that, right? So if you put your hand and stop it, like if you put your hand straight and stop it with your palm, just like that, without catching it or anything, it will hurt a lot. That is why when you're just standing and a cricket ball hits you, it's going to hurt you because it just stopped like that, and all that force turned into, came onto you, whatever place it hit you, and that turned into pain, right? But why? How come it's very unlikely for fielders or anyone who's receiving the ball to get hurt? That is because they use physics. Even cricketers use physics. So if you think, oh, physics is no use for me, physics is useful for everyone. Alright, even cricketers use it. So physics is useful. Alright. So why do fielders do that? Why do they do that? Because that will reduce the force with which the ball is traveling. Because the time is increasing. If once they catch it, before they let it come to a halt, they slowly take it to, like if they're catching it here, if their hand is here, they will slowly take it to the side of their body, right? Just imagine someone catching it and they will take it to the side of their body and stop it there. They won't just catch it and stop it. I mean, there are many situations where they're like aiming for a catch out and then they catch it just like that and then they throw it back into the air and start celebrating. But that's not what I'm talking about. I'm talking about when you're casually passing from one fielder to another. That's how they take it, right? Or they pull it to their side, or they just pull it down. Something that will increase the time. So when you increase the time, the force that is being applied, because force is ma and m is by t, so mv minus u by t, it is inversely proportional to time. So force is inversely proportional to time, right? So as you increase the time, the force will decrease. So in order to decrease the force, the bowlers or fielders increase the time. Alright. Same with many other examples. You can find they're very fascinating examples. When I read them for the first time, I thought, whoa, that's how they use physics in every single thing that's happening around us in the world, right? Alright, so this is a numerical that we have here, example 9.1. When you're trying numericals, I encourage you to hide the solution. Just look at the answer, try to solve it by yourself, and once you solve it, remove your hand or the book or whatever you did to hide it, and then check to see if your answer is right. If it is not right, go through it and see where you went wrong. If it is right, even if it is right, go through the answer to see if you could have done the same problem in a faster way. Maybe you could have avoided 2 or 3 steps. That will help you perform faster and with more efficiency in your exam. So even if you get a question right, go through the solution and see. Alright. We have many examples here, and then we're going to talk about the third law of motion. Alright, so the first two laws of motion tell us how an applied force changes the motion, and these two laws provide us with the method of determining the force. Alright, so but the third law of motion states that when one object exerts the force on the other object, the second object instantaneously, like immediately, exerts a force back on the first object. Alright, so when the two forces are always equal in magnitude, so these two forces are always equal in magnitude, but they're opposite in direction. And what are such forces called? If you say balanced forces, great job. Alright, so these forces act on different objects, and they never, they act on different objects, and they never act on the same object. So if I'm holding if I'm pressing a pen, if I'm pressing a table down, the table will also offer a resistance in the terms of physics. It's not so much so that my hand starts flying off the table. No, not that much, but an equal force that we are already resisting because we are applying that same force. But since they're balanced forces, the table won't break or anything if I apply a reasonable amount of force. Alright, so that's how a gun works. Once you fire a bullet, the forward force of the bullet is equal to the recoil of the gun. So when you fire a bullet, your hand jerks back, right? So that force that the bullet carries is equal and opposite in direction. The bullet moves forward, the gun jerks backward, but it's the same force with which the gun jerks backward, and that proves the third equation of Newton's, third of the Newton's three laws of motion. Alright, so another example would be a rocket launch. When a rocket is taking off, it exerts a lot of pressure in the form of flames, right? Whenever the rocket is taking off, you can see a huge bulk of flames. I don't know if bulk is the right word, but you get what I mean, right? So that flame, whatever force the fuel exerts on the ground exerts back on the rocket, and that is what helps it move upward. Alright, that is an application of Newton's third law of motion. Alright, and even this is a pretty common situation that most of us might have seen. When you're getting off a boat, or when you see people getting off a boat, you see them stepping forward, right? But then the boat moves a bit backwards. Why is that? Because the forward force that we are applying by ourselves to move forward will be reciprocated by the boat moving backwards. So the same force, but in the opposite direction. That is why, in order to prevent the drifting away of the boat, there is usually, wherever a boat is planning to stop, if it's like a tourist boat or something, there is a plank of sorts here, and whoever is in charge of taking us in the boat, they step forward first, and they tie this rope to this plank here, so that the boat stays in place. It does drift, but it doesn't drift back into the waters from which you just appeared, right? Traveled, not appeared. Alright, so those are few common and very easy to remember examples. Alright, so that's another activity, 9.4. That looks fun. I never did it, but it looks fun, so go ahead and try it if you can. Alright, and now we're talking about the conservation of momentum. I suppose this is the last topic, but we'll see. Alright, so conservation of momentum. Suppose two objects, A and B, they have the same masses. They don't have the same masses. Two objects A and B have masses MA and MB. Alright, and they're traveling in the same direction. So if this is A and if this is B, they're traveling in the same direction, let's say to the right. Alright, so they have velocities This is MA, this is MB. They have velocity VA and velocity VB. Alright. So if U of A is greater than U of B, I mean V of A. Oops, my bad. If V of A is greater than V of B, then the two balls will collide with each other because this is moving at a faster rate than this. So if this is moving at 5 meters per second, whenever there are such problems, I imagine like a line. Alright. So this is moving at 10 meters per second, let's say. This is moving at 5 meters per second. Pretty quickly, I mean in a short amount of time, A will overtake B. That is how overtaking works when you're driving, right? If the person in front of you is driving slower than you, you have a good chance of overtaking them. What does that mean? You have a good chance of going in front of them and moving out. Moving faster, right? But if objects, non-living objects, which do not have a continuous control like drivers for a car, they collide. They just collide because B is being left unchecked and it is moving very slowly. A is also being unchecked, but it is moving too fast for B. It's not giving B enough time to move out of A's way. So A will collide with B and they will both collide with each other, essentially. Alright? But if A and B are moving, if they're moving in the same direction, also they collide because sooner or later they're bound to meet each other, and when they do, they're going to hit each other. Alright. So we have the third situation in which A and B are moving with the same velocities and they have the same masses. In such a case, they will keep moving until a resistive force that is acting against the direction of their actual motion stops these two balls from moving. Alright. So once they collide, they transfer that momentum to one another. Alright. So that is how momentum is always maintained constant. Alright. So from figure 9.1, that's the first figure. From equation 9.1, the momenta, that's the plural of momentum. Momenta of ball A before and after collision are mu and mv. Alright. So before collision, it's moving with so in these three situations that I just explained to you, let's consider the first situation, alright, in which A is moving faster than B. So alright, let's say it's a straight line here, and I drew two objects A and B. They have two different masses. They have the same mass, so M and M. So initially they're moving with velocities u of A and u of B. U of A is greater than u of B. So since they're moving in the same direction, B is not moving fast enough for A to move, right? So A and B will collide with each other, alright? And during the collision, they stop momentarily, right? So after the collision again, once they start moving again, let us assume same A and B, same position, same masses, but they start moving with a final velocity v sub A and v sub B instead of u sub A and u sub B. Alright, so v sub A and v sub B are the velocities of objects A and B after the collision, and u sub A, u sub B are the velocities of the objects before the collision. Alright, so what will be the momentum of A and B before collision? So change in the momentum of A and B after collision, what will that be? So it would be m v of a, this is for a, alright. So for a, it would be m v of a minus u of a by t, and for b, it would be m v of b minus u of b by t. Alright. So according to the third law, the force AB, so the force that AB, the force that A exerts on B will be equal and opposite to the force that B exerts on A, right? So, let's see. This is the force that is exerted by A and the force that is exerted by B. So, FAB is equal to negative F of BA. Alright. So, when we substitute them for these, let me get rid of this because that's making it chaotic. Alright. So, when we are taking the difference between these two momenta, we find when we substituting the two momenta in this equation here, we find m v of a minus u of a by t is equal to negative m v of b minus u of b by t. Alright. Okay. So, once we're done with that, if we expand that equation, which is m v of a minus v u of a by t is equal to negative m v of b minus v of u of b by t. And once we expand that, we will get m v a minus m v u if we cancel out the t's, because they're in the denominator. There's no point in them being cross multiplied and all of that, right? mv2 is equal to negative mvb plus mub. Alright. So, based on this, what do we know? That mva plus mvb equals mua plus mub. And when we say it in words, what does it mean? The momenta of objects A and B after collision is equal to the momentum of A and B before the collision. And what does that prove? That the momentum did not change at all. Before and after collision, the momenta of both A and B remain the same. And what does that tell you? That the momentum was conserved throughout this drama, whatever that happened here. Alright. So that proves the law of conservation of momentum. It's a very easy derivation. As long as you understand what you're doing, and as long as you as long as you, I guess it's just understand what you're doing and try to keep track of what you're doing, you will be very good. Alright. So, a result of this ideal collision experiment, this was the experiment that was carried out to put forward the law of conservation of momentum. Alright. We can say that the sum of momenta of the two objects before collision is equal to the sum of momenta after the collision, provided there is no external unbalanced force acting on them. So this is like this tiny terms and conditions apply thing that we see on advertisements and all of that, right? When are the two momenta of A and B before and after the collision equal? When there is no external unbalanced force that is being applied. Alright. So we have a few more activities here and a few examples. Alright. And by examples, I mean they're all numericals. Alright. So such questions are they're very creative, I would say. So they require a lot of analysis um, and planning as to what you want to do, what step after, what step you're going to do to reach the answer. It's a very interesting and fun example. This one and the one previous, the one prior to this, the previous example, they're very interesting, and I used to have fun solving them when I was doing NCERT 9. Alright, so we have a few more questions here. We have about 4 questions, alright, that I want you to try on your own, and if you are unable to do solve one of them, any of them, go back to the video and see where I explained that concept. Once you find it, play it from there, take notes, make sure you understand them, make sure you understand the concept, come back to the question, do it, and once you're done with that, you are ready to move on. Alright, so we have conservation laws. All conservation laws, such as the conservation of momentum, energy, angular momentum, charge, etc., even mass, they're all considered to be fundamental laws in physics. So the laws of motion, the law of gravitation, all those are different, what do they call it? They're complicated or secondary, not primary. They're not exactly complicated, they're just secondary. They're not the basic laws, right? So they're not basic, but the law of conservation of mass, energy, momentum, charge, they're all basic laws. Alright, so it is important to remember that a conservation law cannot be proved. It can be verified or disproved by experiments. That is why we are trying to derive the equation. We are not trying to prove it. And why can't we prove it? Because the external factors in the environment where we experiment these, they are not favorable for proving, and we're better off doing the theoretical analysis and breaking down concepts to understand what's happening. It's easier, and it's I would say it's just easier to do it theoretically than to control every single factor of our environment to make sure the experiment works out, right? So such laws, the basic laws of physics, they cannot be proven very easily. They can either be verified, like how we did it with the ideal collision experiment, or they can be disproved by experiments. You can say this is definitely not what whoever came up with it thought the results of this experiment would be. Then you can disprove that law by providing good evidence that you are right and that person, whoever put forward the law, is wrong. Then the law will be disproved. But there is no way for us to prove the basic laws of physics, because everything, all the assumptions, all the assumptions that we make are based on these basic laws, and so you can't make any assumptions when you're trying to prove basic laws. I think that's also part of the reason why you can't prove the basic laws. Alright, so the law of conservation of momentum that we studied in this lesson, that has been deduced from a large number of observations and experiments. They just didn't do one experiment, they didn't just do one experiment, and they didn't sit and find out the momenta of objects A and B before and after collision for once, and then say, oh yeah, we found out an analogy here, so we're going to go with the law of conservation of momentum. That's not what happened, right? So they performed a large number of observations and experiments before they came to this conclusion, right? And this is a very old law, and by old I don't say it's old as in a negative way. It's awesome how laws that were proved 3 centuries ago are still being followed these days, and they're still being accepted these days, right? So That is about the law of conservation of momentum. And we have reached the end of the chapter where we have what you have learned points. These are good for going through the day before your exam or the day of your exam, right? And once you feel you're confident with the whole chapter and all the concepts, I want you to try the exercises. Alright, we have exercises, and then brace yourself because we also have additional exercises. Because why not, right? No, it's just for more practice so that you can be more familiar and more confident with the concept, alright? So once you are done with that, let us move on to points to recap. Alright, so it is time for points to recap. Alright, think of this very catchy music that we can put here. Points to recap, and then some very nice music, right? Okay, so we introduced the chapter with a question. Supposed to be that. With a question, and I asked you what causes motion in objects. The answer was force, right? And that's how we introduced the chapter. Then we talked about the balanced and unbalanced forces. We talked about the first law of motion, in which we talked about inertia and mass. We talked about the second law of motion, in which we talked about the formula for just force, not gravitational force. Not yet, not yet. Alright, that's the next chapter, right? So that's what we learned in the second law of motion. Then we learned about the third law of motion. Every action has an equal and opposite reaction. That cliche law of motion, right? Whenever they say Newton's law of motion, everyone, when we were young, we used to say, oh, Newton's law of motion, every action has an equal and opposite reaction, right? So that's a very cliche and very well known. That's an advantage for us because it's well known, right? So that's a very well known law of motion. Then we learned about the conservation of momentum with the ideal collision experiment. That was the experiment that we did, and we derived the law. I mean, we proved theoretically, we verified the law, alright? And then we just scrolled through exercises and additional exercises, alright? With that, we are done with the chapter force and laws of motion. Alright, so before you leave thinking that the video is over, it's not. Alright, I hope you enjoyed this video. I hope it helped you understand better, right? And do not forget that you can do this. Alright, have a great rest of your day. Do not forget to like and share the video. Subscribe to our channel for more content, and all the very best. You can do this, and have a safe rest of your day. Bye bye.